So the last thing we want to look at here is multiple roots. So when we factorise the linear function, but it might be to a power of 2 or power of 3 or something like that. Now here's the theorem. If the polynomial does have a multiple root of multiplicity, and I'm just calling it m, so it might be 2 for a double root, 3 for a triple root, whatever, then the derivative will have that same root, but its multiplicity will be 1 less. So if it's a double root, then its derivative will have it as a single root. If it's a triple root, then its derivative will have it as a double root, and so on. Let's prove it. So if we can factorise it, we know x minus a is a root. It'll be to the power of m, whatever that multiplicity is, and it'll be times some other polynomial. But what we do know about that other polynomial is that a is not a solution to it, because then it wouldn't be a multiplicity m, it'll be multiplicity m plus 1 maybe. And m, of course, has to be bigger than 1 because we want it to be a multiple root. Let's differentiate. Right, write down the first, diff the second. Well, best we can do is q dash. Plus, write down the second, diff the first, anarchy. Bring down the power, lower the power, diff the inside. But amongst all that, we can see we do have a common factor of x minus a, and we always take out the lowest power. So it'll be x minus a to the power of m minus 1. So it certainly has a factor to a power of 1 less. But now what we have to see is inside those brackets that it's not a factor of that. So what have we got inside the brackets? Well, it's certainly a factor of the first term, because there it is, x minus a times the derivative. But is it a factor of m times qx? Well, it's not, because we said a is not a root of qx. So we know we could not pull out another factor of x minus a there. So we could write it as x minus a to the power of m minus 1 times some other polynomial where we know a is not a solution to that other polynomial. And so there's our proof. Therefore, the derivative has a root of x equals a, and its multiplicity is 1 less. So now we've got this extra piece of information. We've got a cubic, we know it has a double root. Let's factorise. We've got x cubed minus 4x squared minus 3x plus 18. Now, of course, I could use my factor theorem and go from there. But they've told me it's got a double root. So let's differentiate, because, of course, quadratics are easier to factorise than cubics. Now, if I factorise this one, I get 3x plus 1, x minus 3. I've got two factors here that are single roots. They won't both be double roots, because if they were, then I'd have a quartic, not a cubic. So it's only one of them could possibly be it. Question is, which one? It's either going to be x equals minus a third or x equals 3. We make sensible choices. I'm going to discount that one straight away. It's not likely that's going to be it, because if it was, then the factor would be in the form 3x plus 1. But my polynomial is monic. Now, of course, because it's an equation, I suppose I could multiply everything by 3, and maybe I do end up with that. But what I'm saying is, it's not likely. It's more likely it's going to be the other one. So I'll try the other one. Let's see what happens. X minus 3 squared. Oh, I did it in my head. All right. X equals 3. All I've got to do is substitute it into the first one and confirm that it works. So 3 cubed, 27, 3 squared, 9, 4 nines, 36, 27 minus 36 is, of course, negative 9, minus 3 times 3, minus another 9, negative 18, plus 18. Yeah, we got 0. So we're right, that is the double root. How do I get the other factor? Well, again, I can say leading term times leading term. The leading term in that first factor is actually x squared if we were to expand it out. So it'll be times x. And the constant, if I was to expand that out, I'd have plus 9. 9 times 2 is 18. There's my other factor. So solve the equation, x equals minus 2 or x equals 3. There are only two solutions to the equation. Had this question mean find the roots, then there would be 3 answers. 2 of them would be the same. I'd say, oh, well, the roots are negative 2, 3, and 3. Because it's a double root, it's there twice. So make sure you know what they're asking. Is it just solve the equation, or is it asking what are the roots? 1991, extension 2 HSC. Let's have a look at this for an example. So x equals alpha is going to be a root of this quartic. And you'll notice it's a lovely quartic. The coefficients are palindromic. Looks beautiful. And they've given us this extra piece of information. The first part of the question was, show that alpha cannot be 0, 1, or -1. I'll just use the factor theorem. Look, polynomial 0. If I sub 0 into that, I get 1. 1 is not equal to 0, so 0 can't be a root. So alpha can't be 0. Let's try it with the next one. Polynomial 1. I get 1 plus a, 2a plus b plus 2. Well, I don't know what a and b are, so I have no way of knowing whether that's 0 or not. I'm stuck. Oh, well, let's look at -1. Let's see what happens. Oh, a similar thing ends up happening. -2 plus b plus 2. That's where the other bit of information now becomes useful. Hang on a sec, they told me 2 plus b squared cannot equal 4a squared. Well, that means that 2 plus b can't equal plus or minus 2a. So plus or minus 2a plus b plus 2 can't equal 0. Oh, hang on. The first one was plus 2a plus b plus 2. Well, we just said that can't equal 0. And minus 2a plus b plus 2, that can't equal 0. We got it. So they can't equal 0, so therefore alpha can't be plus or minus 1 either. So, interesting question there. So the 0 was quite easy to find, but 1 and minus 1 proved a little bit tricky. But you had to really read the question carefully to work out how the heck am I going to show this is going to be 0 or not. Okay, we're now going to show that the reciprocal of alpha is also a root. Well, I'll sub that in. What do I get? 1 on alpha to the power of 4 plus a on alpha cubed and so on. Well, let's write that all as one fraction. But have a look at the top of the fraction. That is polynomial alpha. But we said alpha was a root. So polynomial alpha must equal 0. Oh, in that case, polynomial 1 on alpha equals 0. So if alpha is a root, so is 1 on alpha. Now that's interesting. And in fact, that will always be true if the coefficients are palindromic. That'll always happen. If alpha is a root, 1 on alpha will be a root as well. So that's what we've just shown. Okay, so we're going to deduce that if alpha is a multiple root, its multiplicity has to be 2. Right? It's got to be a double root. Can't be a triple root, can't be anything more than that. Got to be a double root. And then just for fun, we're also going to show that 4b is 8 plus a squared because, hey, it's a fun thing to do. Remember, alpha is a double root. So we're saying if alpha is a multiple root. So I'm saying if alpha is a double root, well then so is 1 on alpha. Because what we just said is, if alpha is a root, 1 on alpha is a root. So if alpha appears twice, 1 on alpha must appear twice. So alpha is a root, alpha is a double root, then so is 1 on alpha. Well, that's 4 roots. But we've got a quartic. I can't have more than 4 roots. So there's no way it could be a triple root. Because if it was a triple root, 1 on alpha would be a triple root as well. I'd have 6. Well, I can't have 6, it's a quartic. So if it is a multiple root, then it's got to be a double root. No roots can have multiplicity greater than 2. So neither can alpha be greater than. Now let's have a look at the other bit. 4b is equal to 8 plus a squared. Well, we've just proved that alpha is a double root, so I'll differentiate it. I know alpha is a solution to this. Okay. So I'm going to let the roots be alpha, but hey, 1 on alpha will be a solution as well. Because we said, if alpha is a root, so is 1 on alpha. Okay. Beta will be the third one, whatever it happens to be. Sum of the roots 1 at a time will give me minus 3/4 a. Sum of the roots 2 at a time will give me 1 plus alpha beta plus beta on alpha. All right. And sum of the roots 3 at a time will just give me that beta is minus 1/4 a. Okay, well that's nice at least. I can eliminate the betas. So if I substitute that third one, so the beta, and put it in the first one, in other words, let's eliminate beta out of that first one. I end up with this. Alpha plus 1 on alpha is minus 1/2 a. All right, let's eliminate it out of the other one. If I substitute it into the second one, And look what happens. So the second one, I'll end up getting 1 minus a quarter A alpha minus a quarter A 1 on alpha is a half B. But here's what I did. I factorized the minus a quarter and I'm left with alpha plus 1 on alpha. We just said alpha plus 1 on alpha is minus a half A. So I'll substitute that in and I'll get rid of the fractions and the result drops out that they're looking for. 8 plus A squared is 4B. 10G, 10H, oh, bit of a point here. When it comes to graphs, if you've got a tangent to a cubic and it's only got 2 solutions, so in other words, one of the solutions must be a double root, well, here's the picture. The double root is going to be the tangent. The single root will be where it cuts. It's exactly the same as what happens at the x-axis. Now, whilst we didn't say it in these terms, if you think about it, when you're looking at the x-axis, it's like saying, what's the point of intersection of the line y equals 0 with this curve? And we said, oh, well, the x-intercepts will behave like the roots. So if it was a double root, it'll be like a parabola. It'll touch. If it was a single root, it will cut. Well, that's the same for anything. So just because that's not the x-axis doesn't matter. It's a line going to that. So if it's just touching, then that must be a double root. If it's cutting, that must be a single root.